Welcome back to lectures on engineering mathematics 2, and this is module number 2 on complex analysis, lecture number 12 on differentiability of complex functions. So, in this lecture we will be talking about the continuity of complex functions, and then we will come to the main topic of differentiability, analyticity, etc. So, coming back to just to recall that what is the limit of functions of a complex variable, we call that this limit here as z approaches to z 0 of f z is equal to w z, when w naught is the limit of f z as z approaches to z 0 if. So, this is the first version. So, there were two versions discussed in previous lecture. So, if the difference in the absolute value of this f z and w naught can be made arbitrarily small by choosing z close enough to z naught. So, that was the one definition we understood about the limit, that if the difference of the absolute value this f z and w naught can be made arbitrarily small, then we call that the limit of this f z as z approaches to z naught approaches to w naught. And the second part was that if and only if for given epsilon. So, this was more mathematical way of expressing it. So, if and only if for a given epsilon there exists a positive number delta such that this difference f z and minus w naught, whenever it is less than epsilon, this is less than epsilon whenever we have z from this delta neighborhood, delta minus z minus z naught less than delta. So, we have one neighborhood here. So, if we choose a point z from this delta neighborhood, then the f z should lie in the epsilon neighborhood. This is the idea of this mathematical definition, that we can choose any epsilon. So, for any epsilon there should be a delta, there should exist a delta such that if we choose z from this delta neighborhood, the f z should lie in this w naught neighborhood. So, this was the idea of the limit, and now we will relate this limit to the continuity of f z at a point z naught. So, coming to the continuity of functions of a complex variable, what we say that a function f z is said to be continuous at z equal to z naught if the first condition is that the limit f z as z approaches to 0, let us say this is w naught, meaning that the limit should exist. So, the point here is that the limit f z as z approaches to z naught should exist. If it does not exist, we cannot talk about the continuity of this function at z equal to z naught. So, this limit should exist, and the second is that f z should be defined at z 0, indeed around z 0 also, otherwise we cannot talk about the limit. So, f z must be defined at z naught, that means this f z naught exists. Just not that for getting this limit f z may not be defined at z naught, but for continuity the f z must be defined at z naught, and this f z naught must be equal to the limit w naught, which we have just discussed in this point 1. So, the w naught must be equal to f z naught. So, if we have these three conditions fulfilled, meaning that the limit of f z should exist at z approaches to z naught, the second is the f z must be defined at f z naught, and the value of this f z naught must be equal to w naught. Alternatively, we also can define this, or it is equivalent to say that the function f z, which is u x y plus I v x y, is continuous at the point z naught equal to x naught plus I y naught if and only if the functions. So, this u and v, the components here of this f z u and v, they are continuous at this x naught y naught point. So, this is another way, or we can easily define this continuity in terms of these functions of two variables u x y and v x y. If they are continuous at a point x naught y naught, then we call that this function is also continuous at this point x naught I y naught. So, this is what we call continuity, and there is a so called terminology on removable discontinuity. So, what is this? So, if this limit exists, so this first point which we have defined there, so the limit exists, but it is not equal to f z naught, that means the third one is not fulfilled here, that this f z naught is not equal to the limit which we got with this f z as z approaches to z naught. So, we call then this such a point z naught a removable discontinuity, a point of removable discontinuity, since by redefining f z naught. So, if we just redefine the value of the function at that particular point z naught to be same as the limit, then the function becomes continuous. So, this is what we call removable discontinuity. As such, the function is discontinuous, but if we redefine the function at a point z naught, then this will become continuous, because the limit already exists and we have defined this function in such a way that the function value at this point becomes exactly equal to that limiting value, that limit. So, then the function becomes continuous, and we can then we say that this is a kind of removable discontinuity, means this is a discontinuity, but can be easily removed. Well, so just a simple example to discuss this continuity. So, we have this function which is defined as this I z cube minus 8 divided by z minus 2 I, and whenever z is not equal to 2 I, when z is equal to 2 I, because z is equal to 2 I, this z minus 2 I will become 0, and then the function is not defined. So, at z equal to 2 I, we have defined this here minus 10 I. So, we want to see whether this function is continuous or not. So, we have to basically get the limit of this function f z as z approaches to 2 I. So, to get this limit, just look at this expression here I z cube minus 8 and z minus 2 I. The simple way of getting this, because we can easily identify here that we have z cube, we have here 2 cube. So, if we can use this formula a minus b cube, which is a minus b, and then we have a square b square plus a b. So, if we can use this, perhaps this factor will be cancelled, and then we can pass straight away the limit without any difficulty. So, to do this, we have written just this 8 and I 4. So, the I 4 is nothing but it is a 1. So, we are not disturbing the expression. So, we have I z cube minus 8 I 4 and z minus 2 I, and if we take this I common from this numerator, then we will have this I and then z cube minus this 8 I cube, which we have the form this a cube minus this 2 I whole cube. So, that we can expand now to get this z minus 2 I, that is the factor we got here, and the second factor is remained with this z square with 2 I square. So, 2 I square will become minus 4, and then the product, so 2 z I. So, this is has to be divided by this z minus 2 I. So, this term, this factor gets cancelled, which was problematic to pass the limit. So, we have the I and z square minus 4 plus 2 z I, and z approaches to 2 I. So, when z approaches to 2 I, now we can just substitute this and we will get the limit. So, we have I and z square. So, 4 I square, that is minus 4. Here we have minus 4 already, and z is replaced by 2 I. So, 4 I square. So, again minus 4. So, we have minus 12 I, the value of the limit. But what do we see there, that at z equal to 2 I, the value of the function was minus 10 I. So, this is not equal to minus 12 I, and as a result this function is discontinuous, but this is a kind of discontinuity which can be removed easily. So, if we redefine our function at z equal to 2 I as minus 12 I, then the function will be differentiable, or will be the continuous. So, this is a removal example of a removal discontinuity which we have discussed here. Now, we will move to the most important topic of this lecture, that is actually the differentiability of functions of a complex variable. So, to define the differentiability, we say a function f z is differentiable at a point this z 0 from the set of complex number if this quotient has a limit. So, what is this quotient? F z 0 plus. So, we are talking about the differentiability at z 0. So, we have increment here with this delta z. So, z naught plus delta z minus this f z naught and divided by the delta z, the similar the same definition what we have for real functions as well. So, we have increment there, and we have already discussed for vector valued function, and these complex numbers they have two component x and y. So, we can also think like the vector functions there we have already discussed. So, f z naught plus delta z minus this f z naught, and then we have to divide by this delta z and taking this limit. So, if this limit exists, then independent of the path, that is natural, otherwise we will not call that this limit exists if we have fixed the path and got the limit. So, that is not basically the limit. So, the limit should exist independently of path, that is obvious, and when this delta z approaches to 0. So, this f z is said to be differentiable at a point z naught if this limit exists independent of the path in which this delta z approaches to 0. So, the limit if exists is called the derivative. If this limit exists, that is called the derivative of f at this z naught, and usually denoted by the f prime z naught. So, the standard notations what we are using earlier as well. Okay. So, just to look at a simple example that how to find this differentiability or how to find the derivative. So, find the derivative of this f z equal to z square. So, we will use this fundamental definition that f prime z, if this limit exists, then we can say that this is f prime z. So, we assume that this limit exists because we know in this example the limit is going to exist. So, limit delta z approaches to 0, z plus delta. So, we have taken a general point z here, we did not fix the point. So, z plus delta z minus this f z divided by delta z, and the function is z square. So, this we can replace now the z plus this delta z square minus this z square and this delta z. So, we can open this square there. So, we have z square, then the delta z square, then we have 2 times z delta z, and then minus z square is already there. So, this z square and this z square gets cancelled, and we have here 2 z plus this delta z, and this value and delta z approaches to 0. So, this will go to 0, and we have this value equal to 2 z. So, another interesting example in this theory of the complex variables, we have f z equal to z bar. So, the conjugate of this z, f z is defined as the conjugate of its argument, its input, and this function is not differentiable at any point. This function is not differentiable at any point z in the domain. So, here if we take this limit delta z to 0, f z plus delta z minus f z divided by delta z, if we talk about this function, then this f z plus delta z is given by the conjugate of this z plus delta z minus we have f z. So, which is defined exactly with the conjugate z, and then we have to divide by the delta z and look for its limit. So, that means So, this z plus delta z, if we take the absolute value, the conjugate, then the conjugate, not the absolute value. So, we have the z absolute value minus the delta z absolute value. So, which we have used here, and then we have the minus this z also there. So, this expression, if we look at here, this gets cancelled. So, we have so this was plus there, so not minus. Then we have this delta z, the conjugate, and then divided by this delta z, which is already here. So, now we will look whether this limit exists or not. We will look for this limit now. So, we choose that this delta z approaches to 0 along the real axis. So, we have the real axis here, and we have the imaginary axis. So, we will in the first we will approach this delta z to 0 wherever z is there. So, we will approach to this point along this or parallel to this x axis along this real axis and see that what is the limit. So, along this real axis, if we approach to this 0, that means the imaginary component is fixed. So, we can talk about that along this real axis, this conjugate of delta z, when we are approaching to this point, this delta z, the conjugate will be delta z, because we are talking about now there is a variation in delta x itself, there is nothing in delta y happening. So, we are approaching to this point just by along the real axis. So, this delta z, the absolute the conjugate of delta z is just delta z, and so we have this value as 1, because this will be equal to delta z. So, this is 1, and therefore, the limit along this x axis we are getting as 1. And now, if we approach this along the imaginary axis, so now we are approaching along this imaginary axis. So, this is like the delta z is like I into k. So, there is no x anymore. So, here delta z is equal to I k for some real number k, and then in this situation the limit is going to be minus 1. So, along two different paths we have the value 1 and we have the value minus 1, and therefore, this limit does not exist, and hence this f has no derivative, f is not differentiable at any point in the domain of these complex numbers. So, this is a very special example where we have seen that this z is the conjugate of z is not differentiable at any point in the given domain. Now, here we can just take a look quickly that the differentiability implies continuity. That means, if a function is differentiable, this is continuous. So, we assume that let f be a differentiable at z naught, and we will show that f is continuous at z naught. So, we will consider this expression here, that f z naught plus delta z and minus this f z naught. So, in this case we have f z naught plus delta z minus f z naught, we have divided by this delta z and also multiplied by this delta z, and assuming this delta z is not equal to 0. So, if we take now the limit both the sides, so that means limit delta z approaches to 0, f z naught plus delta z minus f z naught, this equal to this limit into this delta z. And remember that this limit we can break into two parts here. So, the first the limit of this, then the limit of this, and here the first expression here tells if the function is differentiable, this limit will exist. If the function is differentiable, this limit will exist, and then here we have the delta z approaches to 0 and delta z, that is 0. So, something exists there into 0. So, then we have a 0 right hand side. So, that means this is f prime z naught into 0. So, that whole thing is 0. So, this limit here is 0, which implies that the limit delta z approaches to 0 f z naught plus delta z is equal to f z naught, and this is the definition of the continuity. So, this proves that the function is continuous if it is a differentiable function. So, there is extension of this differentiability in the context of this complex variables or complex functions, and we call it like analyticity. So, analytic functions. So, we will just understand now what is analytic functions, what are the differentiable functions we have already seen. So, if the derivative f prime z exists at all points z in a domain D, then f z is said to be analytic in the domain D. So, looking at this now, we do not see any difference on differentiability and analyticity. So, if the derivative f prime z exists at all points z of a domain D, then we also call that f z is differentiable in D, but now we are talking about here that f z is analytic in D. So, what is the difference? So, let me just clear it out. When we are talking about this domain, which is a open domain, usually we consider whenever we are considering a domain. So, here if this derivative f prime z exists at all points z of the domain, then the f z is also differentiable in D, f z is also analytic in D. So, there is no difference as such, and the term regular and holomorphic are also used for analytic functions. The main difference will come when we talk about a point, that f z is differentiable at a point z naught and f z is analytic at a point z naught. Then the real difference of this analyticity and differentiability will come into the picture. So, here the f z is said to be analytic at a point z naught if there exists a neighborhood. Yeah, so that is important, that and this shows exactly that analyticity is little more than differentiability. Differentiability does not imply analyticity, because the function is said to be analytic at a point if there exists a neighborhood at all point of which f z exists, meaning for analyticity f z the function should not only be differentiable at z naught, but it should also be differentiable in the neighborhood of z naught. So, that is the difference where we can understand what is analyticity and what is differentiability. For differentiability at a point, we have just defined that if that limit exists. In the previous slide we have seen that quotient, that limit exists. So, the function is differentiable at z naught, but now for analyticity the differentiability at z naught is not sufficient, but if the function is not only differentiable at z naught, but also in its neighborhood, there exists a neighborhood can be very small, but there should exist a neighborhood at all of these points in the neighborhood, the function should have a derivative, it should be differentiable, then we call the function is analytic. So, there is a well known this Cauchy-Riemann equations, these are called the Shear equation, which are used for verifying that the given function is analytic or not without going through all the fundamental definitions of differentiability, and then we have to, for analyticity at a point, we have to also check whether a neighborhood exists where the function is again differentiable, then only we can claim that this is an analytic function. So, the CR equations help to certain extent to identify that the function is analytic or not. So, here is the statement. So, if f z u x y plus I u y be a function of complex variable z, then the partial differential equations, this u x, the partial derivative of u with respect to x, is equal to partial derivative of v with respect to y, and partial derivative of u with respect to y is equal to minus times the partial derivative of v with respect to x. So, these equations are called the Cauchy-Riemann equations. So, first this is just the definition of the Cauchy-Riemann equation. So, for a function f z u x plus I v y, if we have these two functions, two equations are satisfied, or these two relations are satisfied, and these relations are called the Cauchy-Riemann equations. So, now next, so we have the CR equations. Now, the important result of this discussion is the necessary and the sufficient conditions of analyticity. So, a necessary condition for that this f z be analytic in a domain D is that the u and v satisfy CR equations in D. So, this is the necessary condition that this function will be analytic in a domain if this u and v will satisfy CR equations. So, what do we mean by this necessary condition? It is clear that if these conditions are not satisfied, if CR equations are not satisfied, then this function is not going to be analytic. Indeed, we will see in the proof itself, it is not about the analyticity, if it is also about the differentiability. So, if the CR equations are not satisfied at a point, the function will not be differentiable, or here we are talking about the whole domain. So, if the CR equations are not satisfied in this domain, then the function will not be differentiable, even forget about the analyticity, because analyticity is always more I mean either they have the same notion if we are talking about the domain, otherwise if we are talking about a point, then analyticity is more than differentiability. So, here the necessary condition for differentiability or for this analyticity in a domain D is that u and v must satisfy the CR equations. They must satisfy the CR equations, otherwise this function is not going to be analytic. This is what the necessary condition means. So, this condition will be very useful to prove that a given function is not differentiable or it is not analytic. The second is where we have the sufficient condition, that if we find that the partial derivatives appearing in the CR equations, means this ux, vy, uy and vx, if they are continuous, then CR equations are sufficient for analyticity of f z. So, we have the condition for under which we are sure that the function will be analytic or function will be differentiable. So, these are the conditions that the CR equations, all the derivatives appearing there, these first order partial derivatives, if they are continuous, then the CR equations are sufficient to prove to claim that the function is analytic and definitely differentiable. Just we will go through a quick proof where we will just see the necessary conditions, because the proof for the sufficient condition is a little more involved. So, we will skip here. So, assume that this f z is analytic in D, that is the assumption. That means, the f prime z exists at all points z in this domain D. That means, this quotient has a limit which we are calling a derivative, f prime z exists. Then this f we will write in the component wise. So, u and I v, and then we have v and u x y v x y, and divide by the delta z, which is delta x plus this I delta y, and the limit this delta z approaches to 0. So, since we know that the f prime exists, that is our assumption that f z is analytic, which implies of course that the f prime exists. So, right hand limit should also be same along all the path we take, we approach this delta z to 0, because if this limit exists, then irrespective of the path, the limit should be the same, that is f prime z. So, here we approach through two paths, this delta z to 0, and then we will conclude those CR equations. So, these two paths we have taken, one path is P here, the another path is Q. So, we are in the P, we are first letting delta y to 0, and then we are, so here we have delta y to 0 first and then delta x to 0, and in this path we are letting delta x to 0 first and then delta y to 0. So, these are the two paths. Along these two paths we will approach from this z plus delta z to this z, and we will see that what comes out. So, along this path P, as I said there, delta y to 0, then delta x to 0, along path Q we have delta x to 0 and delta y to 0. So, let us take this expression for the limit, and then along path P. So, first we will let delta y to 0. So, putting there a delta y to 0 first, and then later on this delta x to 0. So, what we will have, we have this expression here. When delta x to 0, this we know and this we know, these are the partial derivatives of u and this v, that means this is u x and this is v x, this is u x and this is v x. So, if this f prime z exists, so naturally this implies here also that u x and v x has to exist, because this limit is equal to u x plus I v x along a particular path, and along any path if we go, the limit should exist, because we know that the limit exists, it should be same f prime z. So, this u x plus I v x is equal to this f prime z, that means this u x and v x both exist. So, the existence of f prime z also shows here the existence of these partial derivatives. Anyway, now we go along with the path q, where dx we will let first to 0 and then delta y to 0. So, in this case again the f prime z equal to this limit, where we have delta y to 0 and delta x is already set here in this case, this delta x 0. So, we have this I delta y there, and we are taking the limit delta y approaches to 0. So, in this case again we will see that here the variation is in y. So, we will get the partial derivative with respect to y when we take delta y to 0, and that I we can adjust with this minus I by multiplying I in numerator and denominator. So, here the delta y, so in this case I goes to 0 and delta y goes to 0. So, this is v y, and then this will go be u y, and we will get minus I there because of this I when we multiply by I and divide by I there to this first expression. So, we will get this equation. So, what do we get? That f prime z has a value u x plus I v x, and also it has a value v y and minus u y. So, these two are same, that, and when two complex numbers are same, so we can compare their real and imaginary part. That means u x must be equal to v y, the u x must be equal to v y, and the other one, the v x must be equal to u y. So, from here we got this conditions that if the function is differentiable at a point, then these two conditions must be satisfied. If these one of these conditions is not satisfied, then the function will not be differentiable at that point, and hence it will not be analytic at that point. So, these are the necessary condition for differentiability or analyticity, and very useful for proving that the given function is not differentiable or it is not analytic. So, here just two quick notes. So, here we have, if the existence of the partial derivative is known, then the following formula can be used for its evaluation, for the evaluation of the derivative. So, if we know u x v x or we know v y u y, just in the previous slide we have seen, if we know that the derivative exists, then this derivative we can compute just directly by having this partial derivative with respect to x or with respect to y. So, this is a nice formula for the getting the derivative without the fundamental definition, for instance. The note 2, the CR equations are necessary condition for differentiability at a point, and they are not satisfied, that f prime z does not exist at that point. So, the function is not differentiable at that point, and CR equations hold at point z naught, then f may or may not be differentiable, because these are necessary conditions, not sufficient conditions. For sufficient condition we need additional restriction of continuity of these partial derivatives. So, if the CR equations hold, then we cannot say anything whether the function will be differentiable or analytic at that point, or it is not analytic at that point. For that we have to go for the further test, that is the continuity of this u x, u y, v x, v y, And so, this CR equations are very useful for proving that the function the derivative does not exist, but for proving that it is differentiable or analytic, we have the CR equations are not sufficient, they are just necessary. Okay, so these are the references we have used for preparing this lecture. And just to conclude here, so we have talked about mainly about the differentiability at z naught, where we can we observe that if this quotient exists, this is then the function is differentiable, and this value is called the derivative of the function. And the function is said to be analytic at a point z naught, because here where the two definitions differ. So, for the function is set analytic if there exists a neighborhood at all points of which f prime z exists. So, the differentiability is little more than analyticity is little more than the differentiability. So, which can be observed this when we are talking about a point. And the necessary condition we have learned for analyticity or differentiability at a point is that these CR equations must be satisfied, and if these partial derivatives appearing here are also continuous, then these conditions become sufficient for claiming that this function is differentiable or even analytic. So, that is all for this lecture, and thank you for your attention.